Four silhouettes in orange suits float inside a pressurized cabin, a mere 9 cubic meters in volume. How does an aluminum shell keep 4 humans alive in the translunar abyss? The precise engineering that transformed the Orion capsule into a safe harbor against the vacuum. Outside the fused silica windows, deep space temperatures swing to absolute extremes, alternating between the scorching heat of sunlight and the biting cold of shadow. The vacuum's silence presses on the outer hull of aluminum lithium alloy with an invisible, constant force. Inside, the uninterrupted hum of fans, valves, and fluid pumps fills the cabin's recyclable air, a constant reminder of their isolation. Every breath from Commander Reed Wiseman, pilot Victor Glover, and specialists Christina Koch and Jeremy Hansen is calculated by computers, filtered by chemical compounds, and returned to the environment. There's no room for mechanical failure when the craft crosses the darkness far beyond Earth's low orbit. Orion isn't just a ballistic transport vehicle. It's a miniature biosphere designed to replace everything our planet provides for free. They are traveling on a continuous trajectory, moving away from home at tens of thousands of kilometers per hour. Their destination is a frontier in deep space where no crewed mission has been in over 53 years. Reaching that 53-year frontier demanded the ignition of 4 main engines beneath the SLS rocket's core stage. On April 1, 2026, a flame tore through the Florida sky, propelling the Artemis II mission out of Earth's gravity. The crew wasn't sent to land on the surface, nor to perform a lunar orbit insertion burn. Orion was precisely positioned on a free return trajectory, a continuous figure-8 flyby, driven solely by orbital mechanics and the moon's gravity. This dictated the mission's exact rhythm: 10 interrupted days in deep space. 10 days where the capsule would be the sole shield between the 4 astronauts, micrometeorites, and solar cosmic radiation. The European service module, docked directly beneath the crew cabin, took on the heavy work of survival. It carries the 4 solar panels that generate vital power, the pressurized oxygen and nitrogen tanks, and the enormous external radiators. These radiators are responsible for dissipating all the heat generated by human bodies and the flight computer banks into the void. Without this constant, millimeter-precise thermal exchange, the cabin would heat the crew in a matter of hours, transforming the craft into a metallic greenhouse. The environmental control system monitors every microscopic temperature fluctuation on the inner walls and within the spacesuits. These inner walls conceal a complex network of liquid cooling pipes and atmospheric pressure sensors. Orion's life support system must contend with a silent, constant enemy that arises from the crew themselves. In the microgravity environment of deep space, gas physics works differently than on Earth. Warm air doesn't rise and cold air doesn't fall. The carbon dioxide exhaled by astronauts with each breath doesn't naturally disperse throughout the cabin. If the main fans were to stop for just a few minutes, invisible bubbles of toxic gas would form around the crew's faces. They would slowly suffocate in the very air they breathe without even noticing the chemical change. To prevent this scenario, Orion maintains continuous forced ventilation designed through rigorous fluid simulations. Stale air is drawn through ducts at the ends of the cabin, pushed through a dual system of solid amine beds. While one bed captures carbon dioxide from the cabin air, the other is exposed directly to the vacuum of space, ejecting the gas outside the craft before returning to the cycle. The humidity generated from the sweat and continuous breathing of the 4 humans is also drawn in, condensed, collected, and separated. Every floating drop of water is a risk that cannot condense on electronic panels or cause short circuits in the navigation consoles. The cabin works frantically to maintain the internal environment in a delicate thermal and chemical balance, while outside, the hull faces the cold radiation of the cosmic void. But the readings from the thermal sensors and oxygen monitors reveal only one part of the daily challenge. The machine needs to sustain human biology, and biology in confinement is unpredictable. What happens when the internal environment itself threatens the crew's survival in the void? The 4 astronauts share a habitable volume smaller than the interior of a commercial cargo van. The noise from the mechanical life support systems is incessant, a high-frequency hum of fans and compressors that never diminishes during the 10 days of flight. The onboard routine is dictated by air purification cycles, cabin pressure monitoring, and communication windows with mission control in Houston. The service module constantly adjusts the solar panel's tilt to ensure the power needed for the air pumps never suffers interruption. There's no gigantic main engine intended to brake the craft and enter lunar orbit, and not enough fuel to abort the mission by shortening the return path. Artemis 2's free return trajectory is an absolute commitment to orbital physics. Once initiated, the engines cannot reverse course. They need to swing around the moon, so the moon's gravity acts as a slingshot, flinging the capsule back toward Earth. And the turning point of this inexorable trajectory led them directly into the shadow of the lunar far side. In the shadow of the lunar far side, Earth's blue light vanished completely from the main hatch window. On April 6, 2026, the Artemis 2 mission reached the human record for distance from Earth, surpassing the historic mark set by the Apollo 13 crew in 1970. The navigation instruments recorded the exact distance of 400,171 kilometers from our planet. For 45 minutes, the radio blackout was absolute. The rocky mass of the moon severed any possibility of communication with mission control. In this telemetry silence, the capsule operated entirely autonomously. The life support system maintained perfectly stable oxygen levels. The radiators continued to dissipate cabin heat into the dark, and the amine valves kept ejecting carbon dioxide into the vacuum. The crew watched the lunar surface pass in silence, approximately 6,550 kilometers below them, a gray landscape studded with ancient dead craters, contrasted absolutely with the mechanical, living pulse within Orion. When the radio signal finally returned on the Deep Space Network antennas, telemetry confirmed that the craft and its occupants had endured the extreme translunar curve. Earth's gravity was already pulling them back, accelerating the capsule toward the intense friction of our atmosphere. The intense friction of Reentry tested Orion's heat shield with temperatures exceeding 2,700 degrees Celsius. The capsule protected the crew not just with thick walls of ablative material, but with an internal mechanical ecosystem that breathed with them for 10 days. The answer to the translunar abyss was a closed loop of air purification, rigorous thermal regulation, and power redundancy. Orion's engineering proved it's possible to isolate and sustain human breath on a flyby far beyond Earth's low orbit. On April 10, 2026, the capsule bobbed in the waters of the Pacific Ocean, awaiting the United States Navy recovery team. The data collected by its life support sensors now define the exact parameters for the lunar landing missions to come in the next phase. A scorched metallic shell cooling in the salt water, guarding the records of what it takes to survive in the darkness between worlds.